This lesson is the final one in section 5.3, and it discusses the method of factoring the sum or difference of perfect cubes. Now, if you recall when we discussed the difference of perfect squares, I said that anytime you have two factors, then you don't have a whole lot of options. The first option is always to take out the greatest common factor, and then if they are perfect squares and they are a difference, you can factor them with the difference of perfect squares, or if they are the sum or difference of perfect cubes, you can factor those. And the reason we can do a sum or difference of perfect cubes in the real numbers is because when we cube a number, it keeps its sign. So if we have a positive number and we cube it, it remains positive. If we cube a negative number, it remains negative. So in that case, we can factor either case. And the way it works out here is the formula that you see here. If you have x cubed plus y cubed, you end up with the factors x plus y, and then the other factor x squared minus xy plus y squared. If you have a difference of perfect cubes, your first term is x minus y, and then your second term is x squared plus xy plus y squared. So if you want to, you can memorize these two formulas. It's a little bit easier if you remember an algorithm, which is you take the cube root of each of these, so cube root of x, the cube root of y, and then from there you square the first term, so you kind of ignore the original problem. You square the first, you multiply them together, and then you square again on the last one. And then as far as the signs are concerned, we usually refer to this as SOAP, meaning if you look at the original sign, then the first sign is going to be the same, the second sign is going to be the opposite, and the last sign is always positive. So, if for instance we want to factor x cubed plus 1,000, and before going through this section, it might be good to go through and recall your perfect cubes. 1 cubed is 1, 2 cubed, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, 5 cubed is 125, and you see how these get rather large rather quickly. 6 cubed is 216, and I remember this because it was the former area code for Akron. 7 cubed is 343, and the way I remember this is essentially you're kind of splitting 7 into half, essentially. So 3, 4, 3, it's symmetric. 8 cubed is 512, and again, if you do anything with computers, that's a common number. 9 cubed is 729, and essentially you have the 72 is 9, and then the 9, and we know any multiples of 9 end up having their terms add to be 9. And last we have 10 cubed is going to be 1,000, so that one's pretty easy. And again, anytime you're taking a power of 10, you just end up with the number of zeros that your exponent is. So if we go back up here and we want to use these formulas to factor x cubed plus 1,000, first thing we do is we check to see if there's a greatest common factor. In this case, there is not. So then we use our formula. We say, okay, we're going to take the cube root of x cubed, which is x, and the cube root of 1,000, which is 10. And we write those in the first set of parentheses. Then with regards to the second set of parentheses, we square the first term, we multiply the two together, which is 10x, and we square the second term, which is 100. 10 squared is 100. Last thing we do is we come through with the signs, same, so this was positive, so same is positive, opposite is negative, the last one is always positive because it's squared. So take a second, pause the video if you need to, and see if you can figure out what I did there. So let's try another example. In this case, again, you always want to take out the greatest common factor if possible. In this case, there is one, and it is 2. And then you are left with a cubed minus 64, which is good because 128 was not a perfect cube. So when you factor out that 2, you are left with 64, which is a perfect cube of 4. So now when we factor, that 2 comes down. Cube root of a cubed is a. Cube root of 64 is 4. For the second set of parentheses, we square the first term, which is a squared. We multiply them together, which is 4a. And then we square the last term, which is 16. Finally, the last step is the signs. So we come through and we say the same sign. So this was negative. Opposite would be positive. And the last one is always positive because it's squared. So I'd like you to pause the video at this point, see if you can try example 36, and then resume the video when you've finished. So in this case, there's no common factors between 125 and 27, so we can go straight to the formula. We take the cube root of 125z cubed, which is 5z. Then we take the cube root of 27y cubed, which is 3y. Then we look at these terms that we found. We square the first one, we square the 5z, and we get 25z squared. We multiply the 2 together to get 15yz, and we square the last term, the 3y, to get 9y squared. The last step is to come through with the signs. It started off positive, so we've got the same. Opposite is negative. Always positive is the last. We've got a few more examples here. If we look at this first example, technically 64 and 8,000 are both perfect cubes, but we want to factor out a common factor if possible. And if you look at this, it actually turns out that 64 is the common factor. So in this case, we factor out a 64, and we're left with w cubed minus 125, because 8,000 divided by 64 is 125. And again, these are nicer numbers to work with. That's why we always take out the greatest common factor first, if possible. So now we are left with 64. The cube root of w cubed is w. The cube root of 125 is 5. We square the first, so w squared. Multiply them together to get 5w. Square the last to get 25. Come through with the signs. We have negative, positive, positive. So same, opposite, always positive. We have one last example here. And the reason I put this example here, there should be a negative sign. The reason I bring up this example is because we've got an a to the 6th, meaning that it is a perfect cube because the exponent is divisible by 3. It is also a perfect square because the exponent is divisible by 2. 729 is also a perfect square and a perfect cube. Anytime you have this type of problem, you want to take the perfect squares first, and you can only do a perfect square if it's negative, if it's a difference, and then do the perfect cubes if possible. So in this case, you say, okay, difference of perfect squares. The square root of a to the 6th is a cubed. The square root of 729 is 27. So you end up with a cubed plus 27, a cubed minus 27, if you look at the difference of perfect squares. And the reason that we do this is because the difference of perfect square ends up with a sum of perfect cubes and a difference of perfect cubes. If we did the difference of perfect cubes first, then we would end up with a term like this that is a lot more difficult to factor. So in this case, the a cubed plus 27, well, that's going to be a and 3 if we take the cube roots. Then we take a squared, multiply them together to get 3a, and cube the last to get 9. Again, if you go through with the signs on the first one, you get plus, minus, plus. Then you have to look at this second set, which is going to produce the same numbers, just different signs. Cube root of a cubed is a, cube root of 27 is 3, a squared, 3a, and 9 are your terms. As far as the signs go, this case you have to go with the negative being the same, then the opposite being positive, and the last one being always positive. So they look very similar, the only difference is the signs. So this concludes the lesson for section 5.3. Now would be a good time to go on and finish up the homework if you've not already started it, and then move on to the video for 5.4.